So essentially what this is going to be is just a review. It's kind of the end of chapter summary. So a lot of people, you're responsible for knowing the mechanisms for all these kind of steps, but sometimes it is helpful just to see kind of everything, right? And if you want to make flashcards or things like that, you still need to know some of these mechanism stuff. So basically what I'm showing here is the basic Grignard or organolithium, sorry, this reactive nucleophiles, these carbanions, reacting with an aldehyde or ketone, right? So this is either, these R's are either both carbons, or one's a carbon, one's a hydrogen. We're doing an addition step, nucleophile, electrophile. Make a tetrahedral intermediate. If you have a tetrahedral intermediate, what do you ask yourselves? Do I have a good leaving group? Carbons and hydrogens are not good leaving groups. So then if you don't have a good leaving group, you protonate. So they're not showing that mechanism here, but you protonate, you get this final product. If it's formaldehyde, a very specific type, right? This means it's an aldehyde that has two hydrogens there, right? Again, no good leaving group, you do the addition step, you do protonation, and here you make a primary alcohol. A Grignard with a formaldehyde makes a primary alcohol. Am I ever going to ask you a question that says, you know, exactly that? No, right? I'm not interested in asking you to memorize that. I want you to be able to draw the mechanism for these things and understand why. If I see, right, you can let's work one of these backwards. A secondary alcohol can come from an aldehyde in a Grignard. Right? A secondary alcohol can come from an aldehyde in a Grignard. A primary alcohol can one way, not the only way, one way. Primary can come from formaldehyde in a Grignard. Right? You gotta know what the terms primary, secondary mean, right? Primary, 2 hydrogens, secondary, 1 hydrogen, tertiary, no hydrogens on the carbon attached to the alcohol. So if you have a Grignard reacting with an aldehyde, addition reaction, tetrahedral intermediate, no good leaving groups, protonation, secondary alcohol. What if you want a tertiary alcohol? Then you react a ketone with a Grignard. Addition reaction, no good leaving group, protonation, tertiary alcohol. And remember, it doesn't have to be a Grignard, right? There's lots of different things, right? Anything that's a strong nucleophile can do this. Grignards specifically, right, make these type of products in this situation with ketones and aldehydes. Okay? What if it's an ester? Ester's a little different, right? Esters are a little different. How are esters different? Esters are different because now, when our Grignard reacts, we do the addition, make a tetrahedral intermediate. Now we have a good leaving group. So that good leaving group is going to leave. So we're going to start with an ester and end up with a ketone intermediate. Ketones are more reactive than esters. Why are ketones more reactive than esters? Ketones, right, can't do resonance. Esters can do resonance. When this lone pair comes, that makes this less delta plus. Right, so ketones are more reactive, so we can't stop there because a Grignard is going to find the more reactive thing, right? Matching reactivity, remember we talked about that. Nucleophile, a more reactive electrophile now. So another Grignard is going to react to that ketone, probably very fast. Addition reaction, tetrahedral intermediate, no leaving group, right? Can't regenerate the carbon, can't do an elimination like we did here. Protonation, another way to get a tertiary alcohol. It's different though because notice, right, we added the same group, whatever our Grignard was, we added that twice to make that tertiary alcohol. So we just talked about carbon nucleophiles, carbanions, right? Things with carbons with a negative charge. We talked about acetylide ions, a triple bond with a minus charge. We talked about Grignards, we talked about organolithiums, things with a negative charge. There's a C minus. There's other things. There's hydrides. What's a hydride? All a hydride is, right, is just an H minus, right? A nucleophilic hydrogen. Hydrogen with, right, a lone pair. There's 2 types of hydrides that you're going to know about. You're going to know about lithium aluminum hydride, right? Lithium aluminum hydride, and sodium borohydride. So 2 types, and they react differently, right? They react differently. And the way they react is based on the periodic trend of size. Right? So I showed a BH bond versus an aluminum H bond. Right, the size of hydrogen doesn't change, but aluminum is bigger than boron. Things that are similar in size are going to be able to share electrons better. It's going to make that bond stronger, less reactive, more covalent bond. So lithium aluminum hydride is actually a more reactive version of hydride. It's not different. It's still H minus. Somebody asked that. That's a great question. Is it different? It's not different. It's just more reactive because of what it's bonded to. Right? It's more available to react with what it's bonded to. So what does that matter? Right? Well, it doesn't matter for some things. Right? So if you look, this is kind of this. We talked a little bit about Mount Carbonyl. You can kind of see it lined up here. Ketone, aldehyde, ester, carboxylic acid. I'd put aldehyde ahead of ketones. But if you put aldehydes and ketones together, they're both pretty reactive electrophiles, right? Neither of them can do resonance. And a ketone has hyperconjugation on both sides, right? Things that are 2 bonds away. Aldehydes only have it on 1, so aldehydes are actually more reactive. But they certainly can't do resonance, like an amide or an ester could. Right? If I stuck in a amide here. So sodium borohydride here will gladly react with a ketone or aldehyde, because those electrophiles are reactive enough that even not a great nucleophile will react. Lithium aluminum hydride, of course, since it's really reactive, will react with a ketone and aldehyde, no problem. But a lithium aluminum hydride will also react with an ester, a carboxylic acid, and the amide. Lithium aluminum hydride reacts with all of them. Right? It's going to react with all of them because it's more reactive. So the less reactive electrophiles, we need a more reactive nucleophile to react with it. You need to match those things up. One thing that is strange, right? And carboxylic acids kind of don't fit here because, right, when I talk about the reactivity of these carbonyls, right, carbonyl is just the carbonyl part for all of these is the same, right? It's the C-double bond O. And what I'm really talking about is the carbon of the carbonyl, how reactive that one atom is, right? Carboxylic acids are weird because, right, they're acids. They're acids first, actually, the carboxylic acids. So carboxylic acids become difficult because really it's this OH bond is probably the first thing that actually reacts. Right, that's the first. That's the most reactive. This is the most delta plus site on a carboxylic acid. So kind of be on the lookout for that. Okay. So here's showing a more complicated mechanism that I expect you to have to do. What I want you to be able to do is basically see lithium aluminum hydride or see sodium borohydride, and you can just basically redraw it as H minus. Now, you need to remember which one you're using, right? So that's when you know what can react with what. But in this case, if you had an ester, like we do here, I wouldn't want you to redraw it like, you could draw it like this, or you could just draw it like this right away, H minus, right? And so that H minus would add in. I'm not worried about you doing this extra step here, this complex. Not asking you to do that. Right, this other one, you can just have another H minus show up, right? Because really, for every, you have 4 H minuses for every one lithium aluminum hydride. So just treat it as H minus the whole time, basically. Don't worry about showing this aluminum oxygen bond here or this aluminum oxygen bond here. Don't worry about that. So the mechanism here is essentially the same as right? This is an ester. Remember the ester with a Grignard? Right? You did 2. Right? It's just now instead of a Grignard, a C minus, it's just H minus. But the mechanism is essentially the same. You add in. Do I have a good tetrahedral intermediate? Do I have any good leaving groups? Yes. Do an elimination. Another H minus comes, adds in. Do I have any good leaving groups? No. Protonation, product. So it's the exact same mechanism, just with a different nucleophile.